Okay, now we have a working perception predictor. In the next, before we studying how to improve the predictor, how to select the one hypothesis in the perception family, let us first have the criteria set up, which is in this part. We want the criteria for which we want to optimize to distinguish poor perception predictors from good ones. This is assessed with respect to the accuracy. For the accuracy, what we need to do is to, for example, to compare the prediction. Let's call this the perception result prediction. We want to compare the prediction with the given value of the target classes at each data sample. Say if the given value, well, is y train. We want to compare y train and the prediction. It is very easy to compare that. In Python, to compare two variables, you use this double equal sample, and it will return a Boolean value, a binary value, true or false. This is false. This is true. NumPy gives a very convenient way of comparing two arrays. Normally, it does not work for two arrays. It's false because this list is not the same as this list. However, what we want to do is to compare each individual elements of those lists rather than as a whole object, whether the two lists are the same, whether the two lists are the same. NumPy gives us this functionality. If you compare two NumPy arrays, it will return us the element-wise comparison. Let's just print this out. I have this true, false, true, false, true, false, as expected. Also, as in many programming languages, the false value will be treated as zeros in NumPy, and the true value will be treated as something that is not be zero. NumPy also gives us a counting function, count non-zero. In this binary, the binary array, then we will have the value, the number of values that turn to be predicted correctly. If we calculate this number of values, the ratio between these values and the total number of samples. The total number of samples has many ways to extract. We have many ways to extract the number from the training data. Where I'm using here is easy. It is just the size of the given annotation. It is 0.6. Which is pretty miserable, but this does not matter. We just need this evaluation. So, and also, we will, instead, beyond knowing the total number of the statistics of making correct predictions and errors, we also want to get at least one individual wrong prediction from the entire training data, and we will use that prediction to improve the model parameter W. Let us just do this. What we will do now is to find out the locations in the binary array. Let's call this binary array is prediction correct. I will have this array. Let's remove this first. And I want to know the locations at which this array has the false value. NumPy provides us a function that returns all the non-zero values in an array, which is NumPy dot non-zero. Okay, let's see what we have. Bear in mind, this is where it's correct, but now our goal is to find out where the prediction is not correct. So do not forget this. Okay, we have this NumPy.nonZero returns us object like that. Actually, this object is a tuple. This tuple contains several sets of indices. The structure is like this. You have a tuple, and in this tuple you have index dim 0. So note that here you have a comma here. Potentially it can have index 1, dim 1, and so on and so forth. Note this comma. I think I have occluded this from the screen. The comma in this part in the result is here. So and the meaning of the result is that, so this is some integer numbers 0, 0, 3, 5, and this is a list of integer numbers with exactly the same length: 1, 1, maybe 2, let's 3, 4. So this means in the array, the first non-zero element is in 0th row, and the first column 0, 1. And there is another non-zero element at 0, 2. And the next non-zero element is at 3 and 3. Okay. Now we only have one-dimensional array. We have true, false, stuff like that. So now the returned non-zero indices has only one array of indices. That is the location of the non-zero, the true values in this vector. Therefore, we need to take out the first set of indices, which is all the indices we need. Okay. These are the locations at which the predictor have performed correctly, has agreed with the given annotation of the data sample. Of course, we need locations where this is not the case. So let's write it explicitly. Is prediction wrong? numpy.logic not, that means to apply the not operator at each location in a vector or in an array. Is prediction correct? Else. Now is wrong. Right? We will need only to look at those samples. We can take a random, because it does not matter which sample we look at. We can take random ones. We can take the first one. It does not matter. Okay, let's take the first one. Call that next index, and call this error in indexes to be this. The next step, we would like to adjust our model parameter w. Sorry, I forgot to remove this. So let me explain the previous steps a little bit. I have renamed this indexes where the model had made wrong prediction as error indices, and I extract the first index to index variable called next I. So then I would like to print out the content of the training sample. Of next I. Okay. This is the content we want to use to update the model parameters. Of course, we would like to set the sign of the direction of the adjustment with respect to, according to the corresponding annotation. Y next Y. Okay, it happens to be positive 1. So let's call this update. And we will update W using this update quantity. Okay. Then what we need to do is to repeat this entire process. I think I'd like to report the error of the training and of the training set. Report C. If you put a letter F in front of a string, it will treat anything in a pair of curled braces as a variable. It will print the value of this variable, and I will give the value of this variable the ratio we have mentioned before. Error indices, we can just take, sorry, not error indices. Count, let's recount the non-zero values. And is prediction correct to y? Okay, okay, that is what we need. So let's do this. Uh-oh, I think I have forgotten size here. Okay, after this update, it seems that we have made nothing, but actually we have updated W. Well, let us see what happened after one step of update. What we need to do is just copy this whole thing and let it execute again. Well, unfortunately, actually this update deteriorate its performance. Well, let's just do it again. See how things goes. Not too much. It deteriorates again. But let's just run a few more times, see how things go. Jump back a little bit. Drop them again. Oh well, an error. Oh yes, of course. But now we have the accuracy to be 100%. The error is because when all the samples has been correctly predicted, it failed to extract the next index to improve the W. The behaviors model look a little bit weird, but it is actually could be explained. If you recall, I don't know, what we have experienced in this example, first the model looks like this, then it identifies some sample with respect to which it will adjust its parameter, then suddenly its behavior changed like that. Actually, it was worse than previously. And then it identifies all those samples as error samples, and by chance it chooses this one to update its parameter, so on and so forth. After iterating for a few loops, eventually, maybe suddenly, it arrives in correct classification boundary. So we will discuss the behavior of the algorithm a little bit later in this course, but that could be expected. But for now, let us make the behavior of the algorithm a little bit more reasonable. Obviously, you do not want to execute code like this. What we do need is a loop. Right? Well, note that in Python you will use the indentation structure defines the relationship structure of the logical structure of the code. So all this block belongs to this loop. And you probably want to avoid this ugly ending of the execution. It failed to find the next data sample using which to improve the parameter. So at this point, let's try to find the next I. Probably like see if error indexes. We want to test its length. Length is a standard Python operator. NumPy's arrays respect the protocol of length. So an array will report its shape in the first dimension as its length. Because this is a one-dimensional array, a vector, aka, so the length is the number of errors the prediction has made on all the training samples. Okay. If there are some errors to update W, then do this. If there isn't, then free, we can break out from this loop. Good. Also, this is the accuracy measured on the training sample. Probably you also want to have a look at the samples which the training process have no access to. By have no access to, I mean the information in the samples are withheld from updating the model parameters. Of course, you have all the right to check out the current model's performance on those samples. Okay, so let's say let's do this. Prediction, validation. Note that I'd like to use the name validation rather than the name test for this kind of thing. I think later we will discuss this process because this test is actually pseudo test. You actually know the correct answer of this test. This test set is you deliberately withheld to check the data, the model performance. It differs from the real test data when you have deployed your model in production environment for which you don't know the correct answer at all. So let's call that validation. We use the perceptron predict x. But I still call that test. And I will use the. I think I'll just do the accuracy rate would be numpy.count non-zero numpy. Oh, I do not do that. I want to count the non-zero predict on valid is the same as the y test. Okay, make the code neat. And I want to report this performance as well. Validation accuracy. Let's see how this goes. Oh, we are fortunate. seems that these two parts of data are very closely linked. Actually, they are linked exactly the same. Does that mean we have made some error bug? So look. Ah, we have made some bugs here. This is too perfect. Okay, we need to report the right thing. Okay, they are well more or less linked, but have some discrepancy. But fortunately, lastly, we have arrived at the correct answer. Here. I now give you a question to think about. This algorithm will terminate when all training errors are correctly classified. Then how about in a situation? Think about this one. If there are some misbehaving samples, for example, a yellow sample, only one yellow sample, just appears here. If here there is a yellow sample, then you will never get zero training error. You have never get the zero prediction error in this set of data, because you cannot look after both part of the yellow sample while correctly classify the purple sample using a straight line in the plane. So if this is the case, and you write the algorithm like this, what will happen? And if you are not happy with what will happen, do you have any solution? And what's the consequence of the solution?